March 1943, Kummersdorf Proving Grounds, south of Berlin. German weapons engineers gathered around a crude metal tube that would change the course of anti-tank warfare. The object on the examination table was not sophisticated. 2 meters of welded steel, battery compartments carved into a wooden stock, primitive wire connections for electrical ignition. Yet this captured American bazooka represented something that would obsess German ordnance specialists for months to come. The weapon had arrived from North Africa, one of several M1 bazookas abandoned by inexperienced American troops during the chaotic early days of Operation Torch. Wehrmacht technical intelligence had shipped it to Germany with urgent priority. Now, under the harsh lights of the Proving Grounds technical workshop, engineers would discover a secret that American designers had unwittingly revealed, a secret that would lead Germany to fundamentally redesign its most successful infantry anti-tank weapon. The examination began systematically. Engineers measured every dimension, photographed every component, weighed each part. The bazooka was disassembled completely, laid out on white sheets, catalogued with Prussian precision. What they found was simultaneously impressive and disappointing. The weapon itself was unremarkable. Simple construction, minimal machining, designed for mass production by workers with limited skills. But the ammunition told a different story entirely. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The 60mm rocket warhead contained something German engineers recognized immediately: a shaped charge. But not just any shaped charge. This was a refined design with a copper liner formed into a precise conical cavity. Upon detonation, the explosive force would collapse this copper cone inward, creating a superplastic jet of metal, traveling at velocities exceeding 7,000 meters per second. This jet could penetrate armor not through kinetic energy or brute force, but through a phenomenon that defeated thickness through geometry and metallurgy. German scientists had been researching shaped charge effects since the late 1880s, when Charles Munro discovered that explosive charges with cavities produced focused effects. By 1938, Swiss physicist Henry Mohaupt had refined the concept into practical anti-tank weapons. Germany had licensed Mohaupt's patents and conducted extensive research at Kummersdorf. The Wehrmacht already possessed shaped charge technology in the form of rifle grenades, demolition charges, and specialized anti-tank weapons. But the American bazooka revealed something unexpected: the simplicity of implementation. The Americans had taken a moderately sized shaped charge, attached it to a stabilized rocket, and created a weapon that any infantryman could operate. The genius was not in the technology itself. The genius was in making that technology deployable at the squad level, without requiring specialized vehicles, complex aiming systems, or extensive training. German engineers immediately grasped the implications. Every American infantry unit could now engage armor independently. Tank commanders advancing across open ground no longer faced only towed anti-tank guns or suicide troops with magnetic mines. They faced soldiers with shoulder-fired rockets hiding in every foxhole, behind every wall, concealed in every tree line. The technical specifications of the American warhead received particular attention. The copper liner thickness, the standoff distance between the liner and the outer casing, the explosive type and density, all of these factors affected penetration performance. German engineers conducted test firings against captured armor plate to measure actual effectiveness. The results confirmed approximately 75 to 100 millimeters of penetration under optimal conditions. This was sufficient to defeat most medium tanks from the side or rear, though frontal armor on heavier vehicles would resist the charge. But here was where German analysis diverged from simple copying. The engineers recognized that while the American concept was sound, the execution could be dramatically improved. Germany already possessed superior shaped charge expertise. The challenge was adapting that knowledge to create a weapon even more effective than the original. The development of Germany's answer would not occur in isolation. Throughout 1942 and early 1943, German infantry on the Eastern Front had been fighting Soviet armor with increasingly desperate measures. The Panzerfaust, which would become Germany's most numerous anti-tank weapon, had emerged from this desperation. Development of the Panzerfaust began in 1942 at Hugo Schneider Aktiengesellschaft, known as HASAG, in Leipzig. The company's engineers, led by Heinrich Langweiler, were tasked with creating a disposable anti-tank weapon that could be mass-produced at minimal cost. The initial concept drew from the Faustpatron, an earlier single-shot weapon that showed promise but lacked sufficient penetration. The first Panzerfaust prototypes used a simple black powder propellant charge to launch a warhead from a disposable steel tube. The design was crude but functional. A soldier would tuck the tube under their arm, aim using basic iron sights, press a trigger lever, and the propellant would blast the warhead toward the target. After firing, the tube was discarded. The entire weapon cost just 3 Reichsmarks to produce. But the early Panzerfaust warheads were relatively small, containing shaped charges with limited penetration capability. The Panzerfaust Klein, the small version, could penetrate approximately 100 millimeters of armor. The Panzerfaust 30, named for its effective range of 30 meters, increased this to 140 millimeters. These were adequate against 34 tanks, but Soviet heavy armor required more powerful warheads. When the captured American bazooka arrived at Kummersdorf in early 1943, German engineers were already developing improved Panzerfaust variants. The examination of the American weapon's shaped charge design provided crucial insights that would directly influence the next generation of German anti-tank weapons. The key revelation was in the copper liner geometry. American engineers had optimized the cone angle, wall thickness, and standoff distance to maximize jet formation and penetration. German metallurgists analyzed the copper composition, finding it was relatively pure with minimal alloying. This purity was critical. Impurities or incorrect alloys could disrupt jet formation, reducing penetration or causing the jet to tumble. German engineers brought this knowledge back to HASAG facilities where Panzerfaust development continued. The technical cross-pollination was immediate. Engineers redesigned the Panzerfaust warhead to incorporate the liner geometry principles observed in the American bazooka. The copper liner thickness was optimized. The standoff distance between the liner and the armor target was carefully calculated. The explosive type was selected for maximum detonation velocity. The result was the Panzerfaust 60, introduced in August 1943. This version featured a substantially larger warhead containing a shaped charge that could penetrate 200 millimeters of armor. The improvement over earlier versions was dramatic, nearly doubling penetration capability, but this was just the beginning. By October 1943, production began on the Panzerfaust 100, which featured an even larger warhead and improved propellant that extended effective range to approximately 100 meters. The shaped charge in this version could penetrate 220 millimeters of armor, sufficient to defeat any Allied tank from any angle at close range. The manufacturing process for these improved Panzerfausts revealed how thoroughly German industry had absorbed the lessons from the captured bazooka. The warhead production required precise metal forming to create the copper liner, careful explosive casting to ensure uniform density, and exact assembly to maintain the critical standoff distance. These were not crude weapons anymore. These were precision munitions produced on industrial scales. HASAG facilities in Leipzig, Muselwitz, and occupied Poland ramped up production dramatically. By late 1943, monthly Panzerfaust production exceeded 100,000 units. By 1944, production reached over 1 million units per month. The total wartime production would exceed 8 million Panzerfausts, making it the most numerous anti-tank weapon ever produced. The human cost of this production mirrored the Panzer Schreck story, though on an even larger scale. HASAG was the third largest exploiter of forced labor in Nazi-controlled Europe. At peak production in 1944, over 60,000 workers labored for HASAG, more than half of them forced laborers and prisoners of war. The company operated 16,581 prisoners in labor subcamps by 1945. At HASAG facilities in Poland, Working conditions were deliberately lethal. Prisoners endured 12-hour shifts, handling toxic chemicals used in explosive production. Exposure to TNT and other compounds caused jaundice, liver failure, and slow poisoning. The yellow skin discoloration from TNT exposure became so common that workers were called canaries by guards who found the poisoning amusing. The Schlieffen camp, producing munitions including Panzerfaust warheads, housed between 2,000 and 5,000 female prisoners with an average life expectancy of 2 months. An explosion there on October 12, 1944, killed 96 prisoner labourers. The blast occurred in a building where workers were filling Panzerfaust warheads with molten explosive. The detonation was heard 15 kilometres away. German officials investigated not to improve safety, but to determine whether production schedules would be affected. The facility resumed operations within 3 days, using replacement prisoners transported from Auschwitz. The workers who died were not listed by name in official records, recorded only as production statistics, casualties measured in lost work hours rather than lost lives. The technical connection between the captured American Bazooka and Panzerfaust development was documented in German engineering reports from 1943. A memorandum dated April 15, 1943, from Kummersdorf to Hassag specifically referenced amerikanische Hohlladungstechnologie, American-shaped charge technology, when discussing improvements to Panzerfaust warhead design. Another report from July 1943 noted that examination of captured American ammunition had bestätigt unsere Theorien über optimale Konusgeometrie, confirmed our theories about optimal cone geometry. The document went on to recommend specific liner angles and thicknesses based on measurements taken from bazooka warheads. The improvements were not simple copying. German engineers had been developing shaped charge weapons independently and possessed deep theoretical understanding. But the American bazooka provided validation of specific design choices and revealed manufacturing techniques that simplified production. The Americans had solved practical problems that German researchers were still working through. One specific innovation concerned the copper liner forming process. American manufacturers had developed a spinning technique that created seamless liners with consistent wall thickness. German engineers adapted this method, replacing their previous deep drawing process, which sometimes created thickness variations that reduced penetration. The new technique improved manufacturing speed and quality simultaneously. The standoff distance between the shaped charge and the target armor was another critical factor the American design illuminated. Too close, and the jet would not fully form before impact. Too far, and the jet would begin to dissipate. The Americans had determined that approximately 2.5 caliber standoffs provided optimal penetration. German engineers confirmed this through testing and applied it to Panzerfaust design. By autumn 1943, the improved Panzerfausts began reaching frontline troops in significant numbers. The weapons were issued with minimal training required. The sights were simple. The operation was intuitive. A soldier could become proficient with just a few practice rounds. This simplicity was crucial because Germany was increasingly relying on young conscripts and older reservists with limited training time. Soviet tank crews began reporting alarming casualty rates. Where previously German infantry had been relatively ineffective against armor without specialized anti-tank guns, now every German soldier was potentially a tank killer. The Panzerfaust's short range required courage, but courage Germany's soldiers still possessed even as strategic situation deteriorated. The tactical impact was immediate and profound. Soviet commanders noted that German defensive positions that previously could be overrun by armor concentration now required extensive infantry clearing operations before tanks could advance safely. Every building, every trench line, every hedgerow potentially concealed soldiers with Panzerfausts. Tank losses to handheld anti-tank weapons increased dramatically throughout 1944. American forces encountered Panzerfausts in Normandy and were shocked by their effectiveness. A report from the 7th U.S. Armored Division in July 1944 noted that Sherman tanks were being destroyed by handheld rocket weapons of devastating power. Intelligence officers initially confused Panzerfausts with Panzerschrecks, both weapons being new to Western Allied experience. The irony was remarkable. American industry had created the bazooka, a revolutionary shoulder-fired anti-tank weapon. German industry had examined it, learned from it, and created something simpler, cheaper, and in many ways more effective. The Panzerfaust required no training infrastructure like the reusable Panzerschreck. It required no electrical system that could fail. It required no aiming sophistication. Point and shoot, then grab another from the supply pile. Production statistics revealed Germany's commitment to the weapon system. In 1944 alone, German industry produced over 6 million Panzerfausts. In January 1945, production exceeded 1,200,000 units despite Allied bombing and advancing Soviet forces. Even in April 1945, with Germany collapsing, factories produced over 100,000 Panzerfausts. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The final Panzerfaust variant, the Panzerfaust 150, appeared in limited numbers in early 1945. This version featured a reloadable launcher tube and improved warhead capable of penetrating 280 mm of armor. Only a few thousand were produced before Germany's surrender, but the design demonstrated how far German engineers had pushed the shaped charge concept beyond the original American inspiration. The technical evolution of the Panzerfaust warhead tells the story of systematic refinement based on captured intelligence. The Panzerfaust Klein from early 1942 used a 44 mm diameter warhead with a relatively shallow-shaped charge cone. Penetration was approximately 100 mm, adequate against early war Soviet tanks, but insufficient against upgraded armor. The Panzerfaust 30, introduced in mid-1943 after examination of American bazooka technology, increased warhead diameter to 100 mm. The shaped charge liner was redesigned using principles observed in captured American ammunition. Penetration increased to 140 mm. This represented a 40% improvement in capability with relatively minor design changes. The Panzerfaust 60 appeared in August 1943, with a 100 mm warhead optimized for the 200 mm penetration. The timing is significant. Just months after captured bazookas arrived at Kummersdorf, substantially improved Panzerfaust variants entered production. The correlation was not coincidental. German documents explicitly reference American-shaped charge designs when specifying the new warheads. A production directive from Hassag dated September 2, 1943, instructed workers to maintain Amerikanischen Konuswinkel, American cone angles, when forming copper liners. Another document specified liner thickness tolerances based on measurements taken from bazooka warheads. The Panzerfaust 100 represented the mature evolution of the design. Introduced in October 1943, it featured a warhead diameter increased to 150 mm. The shaped charge could penetrate 220 mm of armor, sufficient to defeat any Allied tank, including the Soviet IS-2 heavy tank and American M26 Pershing. The propellant charge was also improved, extending effective range to 100 meters. This made the weapon tactically viable at distances where soldiers had better chances of surviving return fire. Earlier Panzerfausts required suicidal courage to employ at 30-meter ranges. The 100-meter version allowed more practical defensive tactics. Production quality remained remarkably consistent despite wartime pressures. Random testing of Panzerfaust warheads showed that approximately 92% achieved specified penetration in trials conducted at Kummersdorf in late 1944. This was extraordinary given the chaotic state of German industry, constant Allied bombing, material shortages, and reliance on forced labor. The quality control reflected German engineering culture even under catastrophic circumstances. Warheads that failed penetration tests were disassembled and analyzed. Copper liner thickness variations were the most common defect, usually caused by worn-forming dies. Explosive casting voids occasionally reduced detonation velocity. These defects were documented, and manufacturing processes were adjusted to maintain standards. Combat effectiveness data from German after-action reports demonstrated the weapon's impact. The 316th Infantry Division, defending along the Vistula River in Poland, reported in September 1944 that Panzerfausts had destroyed 62 Soviet tanks in 2 weeks of defensive fighting. The division had no operational anti-tank guns during this period, relying entirely on handheld weapons. Similar reports came from all fronts. The 78th Sturm Division in Italy reported 41 Allied tanks destroyed by Panzerfausts during October 1944 fighting around Bologna. The 2nd Panzer Division in France claimed 96 Sherman tanks destroyed by Panzerfausts during August 1944 fighting in Normandy. These numbers represented significant tactical impact from a weapon that cost 3 Reichsmarks to produce. Soviet forces captured tens of thousands of Panzerfausts during their advance into Germany. Red Army evaluation teams tested the weapons extensively at proving grounds near Moscow. Soviet reports acknowledged the Panzerfaust as highly effective and simple to operate. Several Soviet sources noted that the weapon was superior to the American Bazooka in terms of penetration and simplicity. The Soviets attempted to copy the Panzerfaust for their own use. Several prototype designs appeared in late 1944 based directly on captured German weapons. However, Soviet industry could not quickly replicate the manufacturing processes, particularly the precision copper liner forming. By the time Soviet engineers solved these problems, the war in Europe was ending. American ordnance experts were equally impressed and concerned. Intelligence reports from First Army in December 1944 noted that the Panzerfaust represented the most serious threat to Allied armour encountered to date. The report continued. The weapon is devastatingly effective at close range and requires minimal training to employ. Every German soldier is now potentially capable of destroying our most powerful tanks. American armor doctrine was modified based on Panzerfaust encounters. Tank commanders were instructed to never advance without infantry support to clear suspected Panzerfaust positions. Artillery preparation before tank advances was increased to suppress or destroy concealed anti-tank teams. Tanks were fitted with additional sandbags and spare track links to provide standoff distance that might defeat shaped charge jets. These countermeasures had limited effectiveness. The Panzerfaust's short range meant users were usually well concealed, difficult to spot before firing. The weapon's disposable nature meant soldiers could carry multiple rounds, engaging several tanks before withdrawal. The simplicity of operation meant even poorly trained Volkssturm militia could achieve kills against experienced tank crews. British forces encountered Panzerfausts during Operation Market Garden in September 1944. German paratroopers defending Arnhem destroyed numerous British tanks using Panzerfausts in close-range urban combat. British after-action reports noted that standard tank tactics were ineffective in built-up areas where every window and doorway might conceal anti-tank weapons. The psychological impact on Allied tank crews was significant. Tankers knew their vehicles were vulnerable to weapons carried by any German soldier they might encounter. This knowledge affected tactical decision-making. Commanders became more cautious, less willing to take risks, more dependent on infantry support. German defenders leveraged this psychological advantage, sometimes using dummy Panzerfaust tubes to deter Allied armour without actually possessing functional weapons. The connection between the captured American Bazooka and German weapons development extended beyond the Panzerfaust. The Panzerschreck, Germany's direct answer to the Bazooka, obviously drew from American technology, but less obviously, shaped charge research for both weapons created expertise that improved other German systems. The hollow charge ammunition for the 88mm PaK-43 anti-tank gun benefited from research conducted during Panzerfaust development. The shaped charge warhead for the Panzerfaust 100 used similar liner geometry to ammunition developed for vehicle-mounted weapons. Engineers working on one project contributed insights to others. The knowledge base expanded across multiple programs simultaneously. German shaped charge research had actually begun before the war. Franz Rudolf Thomanek at the Vienna Arsenal conducted experiments in the late 1930s that demonstrated shaped charge principles. His work contributed to the Panzerfaust, a handheld anti-tank grenade using shaped charge technology. But American practical implementation of these principles in the bazooka validated approaches German researchers were exploring. The theoretical understanding of shaped charge physics improved dramatically during the war. German scientists published classified research papers analyzing jet formation, penetration mechanisms, and liner optimization. One report from April 1944 by Dr. Hubert Schaden at the Reich Institute for Ballistics provided mathematical models for predicting penetration based on liner geometry and explosive properties. This research was remarkably advanced. Schaden's equations accurately predicted that jet velocity was approximately 2 times the detonation velocity of the explosive, a relationship not fully understood by Allied researchers until after the war. His analysis of copper liner thickness optimization influenced Panzerfaust warhead design from mid-1944 onward. The manufacturing infrastructure for Panzerfaust production was geographically dispersed to reduce vulnerability to Allied bombing. Primary production occurred at HASAG facilities in Leipzig, but component manufacturing was distributed across dozens of suppliers. Copper liners were formed at metalworking plants in Thuringia. Explosive casting occurred at chemical facilities in Silesia. Steel tubes were produced at mills in the Ruhr. Final assembly happened at multiple locations. This distribution created logistical complexity, but improved resilience. When Allied bombers destroyed the HASAG plant in Leipzig in December 1944, production shifted to facilities in Muselwitz and Poland with minimal interruption. Total production declined slightly, but never stopped completely, until Soviet forces physically occupied the factories in early 1945. The cost-effectiveness of the Panzerfaust was extraordinary. At 3 Reichsmarks per weapon, Germany could produce over 1,000 Panzerfausts for the cost of a single Panther tank. Each Panzerfaust had the potential to destroy a 40-ton Sherman worth approximately $50,000 in contemporary American currency. The economic exchange ratio heavily favored Germany despite overall Allied material superiority. This economic reality influenced German defensive strategy in the war's final year. As tank production collapsed due to bombing and material shortages, infantry anti-tank weapons became increasingly important. A defense based on dug-in infantry with Panzerfausts could theoretically stop armored offensives without requiring German tanks. This was the logic behind the Volkssturm militia formations equipped primarily with Panzerfausts in late 1944. The reality was less effective than the theory. Poorly trained militia with Panzerfausts could inflict casualties but could not halt determined Allied advances. The weapons were lethal but required soldiers willing to engage tanks at ranges where survival was unlikely. Experienced soldiers could employ Panzerfausts effectively. Frightened teenagers conscripted into Volkssturm often could not. The Battle of Berlin in April 1945 provided the final large-scale demonstration of Panzerfaust effectiveness. German defenders, including Hitler Youth members as young as 14, used tens of thousands of Panzerfausts against Soviet armor in urban combat. Soviet tank losses were heavy, with estimates suggesting over 700 Soviet tanks destroyed or damaged during the battle. Soviet commanders adapted by using massed artillery to pulverize buildings before advancing tanks. Infantry flamethrower teams cleared structures suspected of harboring Panzerfaust teams. These tactics reduced losses but could not eliminate the threat completely. Every street corner, every pile of rubble, every basement window might conceal a Panzerfaust. Soviet tankers pressed forward despite casualties, because the alternative was allowing Germany to prolong the war. The technical documentation of Panzerfaust development survived the war in remarkable completeness. American and British intelligence teams captured extensive files from HASAG facilities and Kummersdorf Proving Grounds. These documents included blueprints, production reports, test data, and engineering correspondence. The captured files provided detailed insight into German weapons development processes. American analysis of these documents revealed the systematic methodology German engineers employed. Every design change was tested, documented, and evaluated. Prototypes were subjected to rigorous trials. Production samples were randomly tested to ensure quality. Even under wartime pressure, German engineering culture maintained standards that impressed Allied investigators. British intelligence published a comprehensive report on German-shaped charge weapons in October 1945. The report acknowledged that German-shaped charge technology was substantially ahead of Allied developments. British researchers noted that Germany had achieved penetration levels with handheld weapons that British scientists believed impossible with charges of comparable size. The report specifically mentioned that examination of captured American bazookas had accelerated German research. A British scientist wrote, "The Germans recognized the potential of shoulder-fired shaped charge weapons earlier than we did, but the American M1 Bazooka provided them with validation of design principles they were exploring. The subsequent German weapons represent refinement of the basic concept to levels exceeding the original." Soviet analysis reached similar conclusions. A Red Army technical intelligence report from June 1945 stated that the Panzerfaust represented the most effective infantry anti-tank weapon of the war. Soviet engineers recommended developing similar weapons for Red Army use. However, Soviet industry focused on improving existing systems rather than copying German designs. The RPG series of anti-tank weapons that appeared in the 1950s drew on Soviet research conducted independently. American post-war weapons development was directly influenced by examination of Panzerfausts and Panzerschrecks. The M20 Super Bazooka, introduced in 1950, incorporated lessons learned from German weapons. The caliber increased to 89 mm, matching the Panzerschreck. The shaped charge warhead design was optimized based on principles observed in captured German ammunition. More significantly, American engineers developed the M72 LAW, light anti-tank weapon, in the 1960s. This disposable shoulder-fired weapon was clearly inspired by the Panzerfaust concept. Single use, minimal training required, issued at squad level. The M72 was essentially an American Panzerfaust adapted for modern warfare. Millions were produced, and the design influenced anti-tank weapons worldwide. The RPG-7, developed by the Soviet Union and introduced in 1961, also reflected lessons from World War II German weapons. While not a direct copy, the RPG-7 incorporated shaped charge technology refined during the war and distributed to squad level similar to German doctrine. The weapon became one of the most widely produced anti-tank systems in history, with over 9 million manufactured. The legacy of the captured American bazooka extended far beyond World War II. By revealing shaped charge technology in a practical, deployable form, the bazooka triggered German weapons development that fundamentally changed infantry anti-tank warfare. The Panzerfaust and Panzerschreck demonstrated that individual soldiers could engage armor without specialized training or support weapons. This tactical revolution influenced military doctrine globally. Post-war armies recognized that concentrated armor attacks could be defeated by dispersed infantry with anti-tank weapons. The massed tank formations of World War II gave way to combined arms tactics that integrated infantry anti-tank capabilities. Armor doctrine emphasized speed and dispersion to reduce vulnerability to handheld weapons. Modern infantry units routinely include shoulder-fired anti-tank weapons as standard equipment. American infantry squads carry AT-4 or Javelin missiles. Russian infantry have RPG-7 variants. British soldiers use NLAW missiles. All of these systems trace their conceptual lineage back to World War II developments, triggered by the American bazooka and refined by German engineers. The human cost of this technological legacy remains incalculable. The Panzerfausts, produced by forced labor at Hassag facilities, killed thousands of Allied soldiers. Soviet tank crews burned alive when shaped charge jets ignited ammunition. American tankers died in vehicles they believed would protect them. British soldiers were killed by weapons manufactured by prisoners who died producing them. The moral complexity is inescapable. The engineering achievement was real. German scientists and engineers genuinely advanced shaped charge technology beyond what Allied researchers had accomplished. But this achievement was built on systematic exploitation of forced labor. The weapons that demonstrated German technical prowess were manufactured by people worked to death in conditions deliberately designed to be lethal. Approximately 35,000 deaths occurred across Hasag labor camps in Poland, though incomplete records prevent precise accounting. These deaths were not accidental. They were the intended result of a system that calculated human lives as production inputs. Workers who became too weak to labor were sent to extermination camps. Replacement workers arrived from Auschwitz and other camps specifically to maintain production rates. The liberation of Hasag facilities by Soviet forces in January 1945 revealed the depth of the atrocity. Soviet soldiers found thousands of emaciated prisoners barely alive, surrounded by warehouses full of completed Panzerfausts awaiting shipment to the front. The juxtaposition was stark. Weapons of extraordinary technical sophistication, produced by people reduced to numbers in a production calculation. Post-war trials addressed some of these crimes. Paul Budin, managing director of Hasag, was indicted for war crimes related to forced labor. However, he died before trial in 1949. Other Hasag officials faced prosecution with mixed results. Some were convicted and imprisoned. Others escaped justice through legal technicalities or lack of evidence. The company itself was dissolved, its assets seized by Soviet authorities. The technical files captured from Hasag and Kummersdorf contained no mention of the forced labor that made production possible. Engineering reports discussed manufacturing processes, quality control, and production rates. They documented warhead performance, copper liner specifications, and explosive compositions. They never mentioned the people who actually built the weapons. German engineers documented everything except the human cost. This omission was deliberate. German technical culture separated engineering achievement from moral consideration. The shaped charge calculations were precise. The metallurgical analysis was thorough. The production optimization was systematic, but the system that made this possible was invisible in the documentation. Engineers calculated tolerances but not suffering. Modern military historians studying Panzerfaust development must confront this duality. The weapons were technically impressive. The engineering was sophisticated. The tactical impact was significant. But the achievement cannot be separated from the means of production. Every Panzerfaust destroyed an Allied tank. Every Panzerfaust was built by exploited labor. Both facts are true simultaneously. The American bazooka that triggered this development was itself a product of rushed wartime engineering. General Leslie Skinner and Lieutenant Edward Ull developed the weapon in just months during 1942. The design emphasized simplicity and rapid production. American industry produced approximately 500,000 bazookas during the war, arming infantry units worldwide. American soldiers used bazookas extensively in every theater. The weapons were effective but had limitations. The 60mm warhead was insufficient against heavy German armor. The battery ignition system was unreliable in cold weather. The accuracy at range was poor, but the basic concept was sound. Infantry could engage armor without waiting for specialized anti-tank guns or artillery support. When German forces captured these weapons in Tunisia, they recognized both the concept's value and the design's weaknesses. The subsequent German developments addressed every limitation. Larger warheads provided better penetration. Magneto-ignition eliminated battery problems. Improved propellants increased range and accuracy. The Germans took an American concept and refined it into weapons more effective than the original. This pattern of technological adaptation was not unique to shaped charge weapons. Germany's MG-42 machine gun drew inspiration from captured Soviet weapons. The Type XXI U-boat incorporated concepts from experimental Allied submarine designs. German jet aircraft benefited from research captured from occupied countries. In each case, German engineers took foreign concepts and developed them beyond the original implementations. But the shaped charge story is particularly significant because the technology transfer was so rapid and the tactical impact so substantial. From first capture of bazookas in November 1942 to mass production of improved Panzerfausts by mid-1943 represents less than 7 months. Few weapons programs have achieved similar speed from concept to deployment, particularly when starting from captured enemy equipment. The complete story of how captured American bazookas influenced German anti-tank weapons reveals the complexity of wartime technological development. Direct copying was rare. Instead, captured weapons provided validation of concepts, revealed manufacturing solutions, and accelerated research programs already underway. The Germans did not simply copy the bazooka. They learned from it, improved upon it, and created weapons that exceeded the original in effectiveness. The Panzerfaust stands as the ultimate expression of this refinement. Over 8 million produced, simple enough for minimally trained soldiers to use effectively, powerful enough to destroy any Allied tank, cheap enough to issue in massive quantities. The weapon represented the synthesis of German-shaped charge expertise, refined through examination of American technology and driven by desperate military necessity. In the final analysis, the captured American bazooka acted as a catalyst. German-shaped charge research was already advanced. Manufacturing capabilities existed. Tactical requirements were clear. But the American weapon demonstrated that shoulder-fired shaped charge systems were practical, deployable, and effective. This validation accelerated German programs and influenced design decisions that made Panzerfausts and Panzerschrecks the formidable weapons they became. The technical achievement was real. The tactical impact was significant. The human cost was unconscionable. All three facts coexist in the historical record. Understanding this story requires acknowledging the engineering sophistication while recognizing the moral bankruptcy of the system that produced it. The shaped charge secret revealed by captured bazookas changed anti-tank warfare forever. But that achievement came with a price paid by thousands who died producing weapons they would never see used. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.